Hello and welcome everyone to week 8 of interactive live sessions for the course on fundamentals of convective heat transfer. The course is being taught by Professor Amaresh Dalal from IIT Guwahati. My name is Debjit. I'm a TA for this course and we shall be solving problems together. So without further ado, let us dive in. So So we have our first question. Uh, the conditions required for fluids to actuate motion in natural convection are. So there are some reasons which really actuate the fluid motion in natural convection where there is no external actuation to the flow. So what are those reasons or conditions required for that? Or rather the causes which affect the natural convection? Is it option A, density gradient in the fluid? Is it option B, the presence of an acceleration field, gravity sort of thing? Uh, is it option C, both A and B, or is it option D, none of the above?
Both A and B.
No.
Both A and B.
Okay.
I think option A only because
Okay. So if we look at the correct answer will be both A and B. The reason for that is that density gradient alone is not enough to actuate the motion. We have to remember the fundamental reason why fluid flow sets in natural convection is due to a buoyancy force. That there are some. Okay, let me try to do it this way. So there is a wall which, let's say, is at a higher temperature than the ambient fluid temperature. Now, what happens is that heat gets transferred from the wall to packets of liquids. Now, let's say if we focus on only a small packet of liquid, so this one got hotter, and as a result, its density reduced. But if there is no acceleration field like gravity, then there is no buoyancy force as such. Buoyancy force is force originates due to the presence of a gravity field, which pulls denser fluids with a higher force and lighter fluids with a lower force. So since this packet of fluid is now resting within another fluid which is denser than it's basically the same fluid, but if we assign different identities to it, so it's a lighter fluid within a denser fluid. Now that would experience a buoyancy force in presence of gravity, and then as a result this buoyancy force would act in this direction, and that would start actuating the fluid flow in this direction. So only density gradient itself is not enough. The presence of an acceleration field is also required. It could not be gravity as well. I could, let's say, take a small container, fill it up with some liquid, and I take it to space where there is no, significant gravitational field of any planet, and there could be other acceleration fields as well. I could tie it to a rope and then rotate it. That would create a centrifugal force in this direction, and as a result, if there is any chance of natural convection being set up, let's say if we have a hot plate like this over here, so then also a natural convection would set up. But in absence of that, natural convection is not possible. Just if I take any isolated container like this, fill it up with a fluid in absence of any acceleration field, and I have some hot plate placed over here. This would heat up the liquid in its vicinity. That density of that would reduce, but that won't set up any current within the fluid. Does that make things clear?
yeah.
Why the acceleration field is necessary? Okay. So moving on to question number 2. So in high Prandtl number fluids, the expression for similarity solution for Nusselt number for natural convection over a vertical isothermal wall is what? Now here you can forget about the numerical part in front of it. Just look at the form and try to identify what it could be.
Option C.
Option C. Okay, so it's 0.503 Rayleigh number to the power 1/4. Any other answer? So this is for the simple case that we know that we have a vertical wall. It's being heated, not heated. It's at it's a vertical isothermal wall. So the temperature of it is held constant. And what else is given? We know that the Prandtl number is high. Okay, so if we look at the solution, it is indeed option C. So simply, the Russell number from scaling analysis, we saw that it would be proportional to Rayleigh number to the power 1/4. And uh, if we now, forget about that scale analysis and dive into a more accurate similarity solution, then also we land up somewhere here, which has the same form. We get the we get a more accurate picture of it. But anyway, the order of magnitude can be predicted from scale analysis alone. Okay, so moving on, we move on to question number 3. So here also we are taking high Prandtl number fluids with natural convection over a vertical isothermal wall. So in this case, what is true? Here the delta is the hydrodynamic boundary layer thickness and delta T is the thermal boundary layer thickness.
Option A.
Option A. Okay. Any other
A,
option? Any other answer?
A.
Option A. So it's a simple one. Option A, the hydrodynamic boundary layer thickness would be greater. So since we know that Prandtl number is much greater than 1, and Prandtl number is, uh, this is proportional to delta by delta t. So this being much greater than 1 means delta would be much greater. Okay, sorry, I did this incorrectly. In high Prandtl number fluids, in high Prandtl number. Okay, am I messing this up? Prandtl number is mu by alpha, and delta is proportional to mu, and delta t is proportional to alpha. So this means delta would be much greater than delta t. That's why option A would be correct. So in the lectures also we saw the diagram. So if we try to draw the diagram of, let's say, uh, okay, we will do two things. This is distance from the wall x, and let's first of all try to draw the temperature profile, or rather the temperature difference profile. So the temperature difference is high over here. It gradually decreases and goes to 0 like this. So okay, we will make this a bit smaller. So temperature difference gradually dies down, and we can call this distance delta t. This is the thermal boundary layer thickness. And if we try to draw the velocity profile, so velocity would be 0 over here at x equal to 0 due to no slip boundary condition, and it would accelerate within the thermal boundary layer, and beyond the thermal boundary layer as well, there would be this layer of fluid which will be pulled along with the accelerating fluid near the wall. So this distance, this we can call delta, and this delta would be much greater than delta t for Prandtl number greater than 1. Okay, so moving on, now the opposite case for low Prandtl number fluids and natural convection over a vertical isothermal wall, what would be the correct relationship between the two boundary layers?
D. B.
Option B. Okay. Any other answer? Okay. So if we look at the correct solution, it's not B. It's rather option C. The reason is uh, actually very interesting. So let's say if we try to draw those profiles once again. So once again, I'll start with the temperature difference profile. So let's say the temperature difference profile goes something like this with X. This is X. And if we try to draw the velocity profile now, so what happens uh, in the vicinity of the wall, there is this, high gradient of fluid velocity, and then it kind of dies down, but it does not go to zero. Rather, as long as there is this thermal boundary layer, mind you, the fluid within this region, this is still receiving heat from the wall, and it's at a higher temperature than the ambient fluid. So as a result, that fluid is also still lighter than the rest of the fluid, and it is still experiencing a buoyancy force, and as a result it is getting accelerated. So this velocity boundary layer also, this extends as long as there is a thermal boundary layer. As a result, the uh, thermal boundary layer and the hydrodynamic boundary layer, they are of comparable order of magnitudes. But however, there is this small region taken uh, within the near vicinity of the wall. We call it delta V. This is not exactly equal to the hydrodynamic boundary layer, but rather we can say that uh, it's the region within which there are high gradients of velocity. So, and this delta V, this is actually much lesser than delta T, and this is where this kind of a relationship would hold good. But as long as the we consider that hydrodynamic boundary layer is a layer of fluid where there is a motion set up due to temperature difference. So then that hydrodynamic boundary layer would extend as long as the thermal boundary layer goes. Does that make sense?
Yes, sir.
Yes.
So I think this is a very remarkable difference between natural convection and forced convection. In forced convection, it could be the other way around. The delta T could actually be much greater than delta. But in this case, as long as there is a temperature difference, there will be some velocity in the fluid associated with it, because due to that temperature difference, the fluid gets lighter than the ambient fluid and experiences a buoyancy force which keeps pushing it upward.
Sir, in the previous case, the fluid which is not affected by the temperature gradient, that is pulled due to the effects of viscosity, right?
Yeah, correct. So if we go back,
So,
yeah,
uh,
either the fluid is accelerated due to temperature difference within this region only.
so then why this hydrodynamic boundary layer
Hmm.
is actually going thickness is going beyond that of
Going
the.
beyond that, because let's say if we take two packets of fluids again over here. So this packet of fluid, this has a high velocity in this direction. So due to viscosity, remember, its high Prandtl number means the momentum diffusivity is also quite high. The kinematic viscosity is quite high. So that high viscosity is actually pulling these packets of liquids far away from the thermal boundary layer as well along with it. So the
Yes, yes, got it.
the region over here, this attains some momentum due to temperature difference. Now that momentum is diffused in the far field as well due to the property of viscosity of that fluid. And since
Yes,
it is high, it keeps extending towards considerable lengths.
Okay, so that momentum that is obtained due to buoyancy force is diffused at
Correct.
a farther distance, you can say, from
Correct.
the plate. Okay, what?
Left side buoyancy and right side inertia effect.
Correct. So inertia is what? Momentum. That momentum is diffuse means there are inertial forces playing a role over there. Okay. So question 4 we did. Okay. So move on to question number 5 of today's session. So Buznesk number. What is Buznesk number given by? Is it
A.
option
A.
A Rayleigh number into Prandtl number? Is it option B Rayleigh number by Prandtl number? Is it option C Rayleigh number to the power 1/4? Or is it D the product of Rayleigh number and Prandtl number to the power 1/4?
First option. A.
First one, A.
First option. Very simple. So it's simply Rayleigh number multiplied by Prandtl number. Buznesk number is given by Rayleigh number into Prandtl number. And what role does it play in low Prandtl number fluids? The Nusselt number is proportional to Rayleigh number into Prandtl number to the power 1/4. We can simply write this as Buznesk number to the power 1/4. Correct.
Yes.
What is the physical significance of this Bosnick's numbers?
Yes.
Sorry, what?
The
What?
physical significance of this
The
Bosnick's
physical
numbers.
significance, it's sort of like Reynolds number in analogous to natural convection. So we saw that in forced convection, the Nusselt number was some function of Reynolds number. Sorry, some function of Reynolds number and sometimes Prandtl number depending on the value of Prandtl number itself. So over here, this is for natural convection and for low Prandtl number flows. This Buznesk number is somewhat analogous to Reynolds number. Not exactly, but kind of.
Yes. But Debjit sir,
Yes.
actually,
Grashof number.
Grashof number into Prandtl number is itself as Rayleigh number. So why we are doing like this? It is Rayleigh number into
Yeah,
Prandtl
yeah,
number square is
yeah.
Helsinki
There
number.
is a significant difference in in forced convection. While we consider Reynolds number, there is some u associated with it, right? So some length scale into u divided by mu. But in case of natural convection, there is no reference u. The velocities themselves are created due to the
Then
temperature variations and temperature variations and density variations and so on. So if we try to find something analogous to Reynolds number over here, we need some u ref, and u ref has no imposed velocity, so to say. So everything is a function of the gravitational field, the temperature difference, the what is that? The bulk modulus and so on. So it's more complicated than that, but somehow this Buznesk number is uh, somehow it is analogous to Reynolds number over here. But since we do not have explicitly u, so that's why that significant difference is there between those.
no.
Okay, so moving on, what is the Richardson number given by? Is it product of Grashof number and Prandtl number? Is it Grashof number by Reynolds number square? Is it Grashof number by Reynolds number? Or is it Rayleigh number by Prandtl number?
Grashof number by Reynolds number square.
B. B.
B. So
B.
option B, correct. So Richardson number is given by Grashof number divided by Reynolds number to the power squared, and the usefulness of Richardson number is that it compares the relative importance of natural convection and forced convection when both are present. So if Richardson number is much less than 1, that means the Grashof number is much lesser than the Reynolds number flow. So in that case, uh, natural convection is much more dominant than forced convection, and when Richardson number is much greater than 1, Sorry, did I do this correctly? Richardson number
Reverse, reverse,
more
reverse.
than once means okay. So this is not right. So forced convection would be uh, Kresov number is less than Reynolds number. So natural convection would be less than forced convection. Correct. So this is the thing, and in this case, natural convection would be more. And in case this is somewhat nearby one, so in that case, both natural convection and forced convection are important. So those cases are called mixed convection or combined convection regimes. So that is the usefulness of Richardson number. Moving on, so if we consider natural convection on a vertical plate with uniform heat flux rather than uniform wall temperature, so then what would be the relationship between the thermal boundary layer and the span-wise length? Is it delta T proportional to y to the power 1/4? Is it delta T proportional to y to the power 1/5? Or is it to the power minus 1 by 4? Or is it to the power minus 1 by 5?
I think it is minus 1 by 4. So
So is
delta
it
T
option C you are saying?
C, yes.
Okay. Any other option? Any other answer?
No, sir, I don't have it.
The heat transfer rate is heat flux is direct of the order of
So this is
whereas
not isothermal case. Here the heat flux is constant.
heat flux is of the order of y raised to uh, minus 1 by 4.
Minus 1 by, sorry?
Minus 1 by 4 heat flux. But
C only, right?
uh, yes,
Okay. Any other answer?
No idea, sir. I haven't.
Okay. So if we look at the answer, it is option B. Delta T is proportional to y to the power 1 by 5. So the one case which has been discussed widely in week 8 was the uh, natural convection on the vertical plate with uniform wall temperature, and in that case delta t was proportional to y to the power 1 by 4 we saw. So basically it won't be any of the negative numbers because see with y is this direction. With y, the delta T would increase because there is a finite thermal diffusivity. So the power of y has to be positive since with increasing y, the delta T will also increase. Now, in the other case, when the heat flux is made constant and not the temperature the wall, in that case, by scaling analysis, it was shown in the last lecture of week 8 that this delta t would be proportional to y to the power 1 by 5. It was shown using scale analysis only. I guess in week 9, similarity solutions of these cases will also be discussed. So go through those lectures. I think these would be made more clear why it goes this way.
yes, yes. It is shown at the
But
end, the third lecture. It is shown.
yeah, but
Yeah.
these would be incorrect by observation only, since we know that there is a finite thermal diffusivity. So with increasing y, the delta T would go on increasing as well. So the power of y has to be positive. Okay. Okay. So moving on to last question of today's session. So let's say we consider a cylinder with radius 3 centimeter and height 30 centimeter, height or length also you can say. So here the actual values are also not of any consequence. The main thing I wanted to highlight is that the height is significantly greater than the radius. So it's not a stout cylinder; it's a slender cylinder. Now it has to be cooled by placing inside a refrigerator filled with cold ambient air. So you can think of this as a can of cold drink, uh, but it's hot. Now I want to cool it before drinking, so I'm putting it inside a refrigerator to cool it. Now there are two orientations in which I can keep. I can either keep it standing in a vertical orientation, or I can place it. I can lay it down in a horizontal orientation. Now, which of these orientations do you think will cool it quicker?
First.
First one, the vertical cylinder. Okay, so what is your reasoning behind that?
Characteristic length.
Characteristic length. Okay, so can you elaborate a bit more?
Actually, the Nusselt number is a function of Grashof number.
Nusselt number is
And
a function of Grashof number.
yes, that is a Rayleigh number actually. Grashof number into Prandtl number. It's a Rayleigh number. And in Rayleigh number, we are having characteristic length cube.
So Rayleigh number is proportional to h cube.
H cube.
This is 1 to the power 4. So basically, it boils down to Nusselt number to the proportional to h to the power 3 by 4.
Because all other coefficient of thermal expansion is beta, G, delta T, nu, alpha, everything remains constant, and it becomes function of only characteristic length. So as compared to diameter, horizontal cylinder LC is diameter, and for vertical cylinder LC is length.
So in this case, I have something like this, and in this case, I have something like this. And since L is much greater than D, this one should be higher, right?
Yeah.
Yeah. So using this simple argument, this is correct, and indeed the vertical cylinder should give or keeping the cylinder in a vertical orientation should cool it down quicker. But in experiments, it is seen that keeping it in the horizontal position actually cools it down more quickly. So what is the reason of that? The reason is,
shall I tell something? If we keep it in the horizontal position, right? So the thermal boundary layer thickness will be less.
Thermal boundary layer thickness would be less. Yeah, correct.
Yes.
Then,
and that's why the heat transfer rate will be more in this case. Means if we think keep aside the thermal boundary layer and all that, if we keep aside the thermal boundary layer and all that, if we see that in case of vertical cylinder, as the air rises up, it will become hotter and hotter. So the upper portion of the vertical cylinder will not lose the same heat with the same rate as the lower portion. So I think the average heat transfer rate will be less in case of the first case.
Correct, very good. So that physical argument actually holds true as well. So let me try to draw a figure and make sure I understood your answer correctly. So this, I'm keeping it in the vertical position, and there is a boundary layer getting formed like this. So if this is more longer, so the delta T also grows thicker, and as a result, the top portion of this tall cylinder, it is less exposed to colder airs. Rather, if I keep it in this position, a significantly large portion of it is exposed to colder airs. As a result, it might cool faster. So that physical argument actually holds true, and indeed, the horizontal position is actually more beneficial in cooling it quicker. And a more mathematical argument is given over here. I'll share the slides. You can have a better look at that then. So the main difference over there is that, see, this is the calculation of Nusselt number over here. There we use the same formula that we know for vertical flat plates. So Nusselt number being proportional to Rayleigh number to the power 1/4. But as we see from more detailed analysis, that in case of a cylinder being placed, horizontally, the expression of Nusselt number is different. It's not proportional. It's not directly proportional to Rayleigh number to the power 1/4. And as a result, if we plug in the values in that complicated, expression, we get a Rayleigh number which is, much larger than what we get for the, vertical orientation. And as a result, the horizontal Nusselt number is not much greater, but at least it's greater by a little bit than the vertical one. So this is a particular example being taken, and it was shown that it was 3% faster in the horizontal orientation. So this is the mathematical argument. The physical argument was actually correct that you gave over here. So being in a horizontal position, it's more exposed to colder airs and the thickness is lower. So the gradients of temperature are also higher. So that actually enhances the rate of heat transfer away from the cylinder.
Is this a case for the plate then?
Sorry, what?
For plate?
Uh, for plate, it would be a different issue, but I guess I'm not sure. But I guess the physical argument also holds true there. Okay.
But then, sir,
No, I think for plate
theoretical.
dimension matters. Means somewhere there is a threshold value which will dimension matters in plate. Here it is 30 centimeter and 3 centimeter. There is appreciable
Yeah.
difference between
Yeah.
diameter
No,
and
that difference is there. We are considering, a finite body with finite dimensions over here. If we consider those infinite flat plates, so in that case, I'm sure the physics as well as the mathematics will be different.
yes.
So we will have to, for this, we will have to look at analytical solutions of, infinite flat plates being kept in a horizontal orientation. There are analytical solutions for this, although it was not discussed in the current course. So if we look at those, we can, have a better understanding of this.
Okay.
Okay. The main thing is the finiteness of dimensions for this cylinder case actually dictates the behavior. Okay. So that's all for today. Thank you all. We will meet again next week.